Okay, so if you follow the syllabus for the course, you'll notice that from the beginning of the semester up to the material we just finished, we were following the order of the chapters from the textbook. Now we're going to skip one of the chapters, which is chapter 7, and we're going to go to chapter 8, which is the topic related to fundamental sampling distributions and data descriptions. So I just want you to have that clear. So if you go study from the book, we're skipping one chapter. So in this chapter, again, we're going to talk about sampling. And some of the topics that we want to cover include statistical inference, random sampling, some important statistics. So we're going to refer back to the statistics we covered at the beginning of the course, the mean, the standard deviation, and so on. The sampling distributions based on the mean and the Central Limit Theorem. We're going to talk about sampling distributions for the standard deviation or for the variance. And finally, we're going to cover the t-distribution. For today, I think we're going to be able to go up to here. So let's see how this goes. So again, in order to go to the computational material or computational stuff of this topic, we need to cover some theory first. So I'm going to refer back to some of the topics we covered already, and I'm going to tie them to what was new. Okay, so I always like to show this slide just to give you an idea of where we are. So you know that we covered this at the beginning of the course. So today we're going to go back to this, okay? But from a different point of view, from a different perspective. We're going to, instead of looking at the sample mean and the sample variance as a number, now we're going to define some distribution for those. So we're going to treat those measures as random variables. So we're going to define some distributions for that. And you're going to see why that is important. So we covered sample, material, and probability. Continuous, we finished continuous distributions. So today we're going to talk about sampling distributions. So this ties to the measure of location, the random variables material, and the probability distribution material. So you're going to need, and you're going to be able to, in order to understand this, you need to have a good understanding about probability distributions, random variables, and measures of location. Okay, so those three topics come together to the material we're going to cover today. So the learning objectives want to explain the general concepts of estimating the parameters of a population or a probability distribution. Also, explain the important role of the normal distribution as a sampling distribution. And finally, I want you to understand the importance of the Central Limit Theorem, which is, again, very important for statistics and for making inference about your sample. So let's start by discussing some, or reviewing these concepts of statistical inference. So statistics is concerned with making inference about the populations and population characteristics. So as I explained earlier in this class, we started by making an inference that we're going to take some information from the population. It's impossible for us, if you're looking at a particular problem, to take into account all the units or the members of the population. So usually what we do in probability and statistics is to take a sample, and from there, we're going to make some inference about the population using the sample. Okay? So far, we were able to make get some information from here, and we study the sample, how to manage the sample. Today, we're going to start a material that's going to go this way. So from the sample, how to make some inference about the population. Okay? So I want you to have that very clear. So now we are moving from here to here. So statistical inference is always focused on drawing conclusions about one or more parameters of a population. So an important part of this process is obtaining estimates of parameters. Okay? So suppose that we want to obtain a point estimate or a reasonable value of a population parameter. We know that before the data is collected, the observations are considered to be random variables. So you remember from, it was the second lecture, or the 10th lecture on this class, we started by discussing when you get a sample, those observations that you collect from your sample, you can define random variables that will give a number or a value to each observation. So for example, if you remember the number of defective, you can assign, if you get a unit from the process and you see that the part is not defective, you can assign a 0. But if it is defective, you can assign a 1. So that means that each member of the sample assumes a value, and that represents the value of the random variable. Okay, so the observations are considered random variables for that reason. You can define a function, you can assign a value depending on how you define that random variable. So each point would define a random variable. Therefore, any function of the observation or any statistic is also a random variable. So by this we mean that you get 10 points or 10 members and you define that as your sample. You can define a random variable for each point of the sample, but you can also compute some statistics about the sample. So if you want to get the mean or the average based on the sample, you can do that. But what will that mean is that that mean will also be a random variable that will depend on the sample that you get from the population. So each member of the sample is a random variable. The statistics that you compute from the sample are also random variables. So for example, the sample mean and the sample variance are statistics that they are also random variables. Okay, so the sample mean will also be a random variable. The mean will also be a random variable. So since statistic is a random variable, you can assign or you can define a probability distribution for the mean. Okay, so let's think about that. So we take we take some sample from the population. That's what we did for the material and probability distribution. And we try to fit the distribution to this sample. Now what we're saying is, instead of fitting the distribution to the sample itself, we're going to compute statistics for, let's say you take 3 samples, you compute the mean for each sample. Those 3 means will also, you can define the distribution for the 3 means of the 3 samples. So you can have a distribution for the sample, and you can also have a distribution for the means of the sample. Okay? And that's the key for this material. So now we're not going to deal with the points of the sample. We're going to deal with the statistics of the sample. So you're going to take 3 samples, you're going to compute the mean, and you're going to define the distribution for the mean, not for the individual sample points. Okay? So that's what we're doing in this material, in this lecture. So I'm giving the example of the mean, but we're also going to do that for the variance. And you will see why that is important. So we call the probability distribution of a statistic a sampling distribution. So the distributions that you will define for the mean are sampling distributions. The distribution that you're going to define for the variance are also sampling distributions. Yes, sir.
In the context of variance and how we're going to use it and be running it, what would you define it as? Because I think variance is just kind of like a range.
The variance will be the dispersion of of your observations. So you want to define how variable, and redundant, right? How variable are your points from the sample? So if you get, let's say, all 100, you see there's no variability in those numbers. So you get 10, 100 points, no variability. But if you get 0, 120, 200, the variability will define how variable are your observations, how dispersed are they, and so on. The range will only tell you the minimum and the maximum difference. But that is not going to tell you about, because you can have a 0, you can have 100, but you can have 20, 50. That doesn't mean that your sample point is very variable.
Say, for instance, you have a sample, you get a 10, 100 score of something. How's the variance going to measure the importance of each sample?
Okay, so we haven't get to that point yet, but what we're trying to do is define what we're going to do first, and we're going to get to that point yet in the few slides. Okay? Okay, so for now, just think about the random variables, and that we're going to treat the mean and the sample variance as random variables. Okay? Good question. So let's talk first about random sampling. In this lecture, we focus on sampling from distributions or populations. So we already provide an introduction to the role of the sample mean and the sample variance. We'll play statistical inference in later lectures. So we're going to again focus on the sample mean and the sample variance. So the totality of observations, finite or infinite, constitute what we call a population. So by definition, a population consists of the totality of observations with which we are concerned. So for example, if there are 600 students in the school whom we classify according to block type, we say that we have a population of what is the size of the population? 600. Okay? So it's the totality of the observation. So the population size is 600. Okay? Each observation in a population is a value of a random variable. So as I explained with the example of the defective, not defective, zeros and ones, you can define a value for each observation in the population. Another example is, well, I think it's going to be the same. So inspecting items coming of an assembly line for defects. Then each observation is in the population might have a value of 0 or 1. So we can define that as a memory variable, which assumes 0s and 1s. So now we know that random variable will have a probability distribution that looks like this. It's a binomial, where 0 indicates a non-defective item and 1 indicates a defective item. So that's something we already know. Okay, we can define a random variable for the observations, and we can find a probability distribution. Now, in statistical inference, we are interested in arriving at conclusions concerning the population, where it's impossible or impractical to observe the entire set of observations. Okay? So for example, if you wanted to determine the average length of life of a certain brand of light bulbs, it will be impossible to test all such bulbs if we are to have any left to sell. Okay, so think about that. So you will not be able to test all of them. You're going to have to test some of them and then find out how the life of the majority, or make an inference about the life length of the light bulb. Therefore, we depend on a subset of observations from the population to make inference concerning the same population. Okay? We depend on a subset of observations to make inference about the whole population. Okay? Can I move next to the next slide? Okay? So, as we defined already in class, a sample is a subset of the population. So, a subset of the population. If our inference from the sample to the population are to be valid, then we need to find ways of getting or finding of collecting those samples properly. So obtain samples that are representative of the population. So, for example, if you need to submit a report about your grades, let's say you have a scholarship and the scholarship asks you to submit your grades for 3 out of your 5 courses. Which ones are you gonna submit? Are you gonna submit the best one, or are you gonna submit the bad one? Of course, you're gonna submit the best one because you wanna show that you're doing well. So, but that way of collecting a sample is not the best because you're not taking a representative. You're just finding the best sample that will benefit for your outcome. So, a sampling procedure that produces inference that consistently overestimate or underestimate some characteristics of the population is said to be biased. So we want to avoid collect samples from the populations that are biased. You want to avoid to have the students submitting only the best grade. You want to be able for the students to submit a representative sample of how are they doing in the class or in the course or the semester. Okay? So to eliminate any possibility of bias in the sampling procedure, we need to choose a sample where the observations are made independently and at random. So from the 5 courses, you're going to select any of the 3 and you're going to submit those 3 courses without looking at the scores, for instance. Okay? So the important thing about this is you want to be able to collect samples from the population, but those samples cannot be biased. They need to be representative of the population in order to get to good conclusions and analysis. Okay? So the last thing about sampling is how to define a probability density function. So if you have x1 to xn independent random variable, each having the sample probability function, f of x, then we define x1, x2, and xn to be a random sample of the size n from the population f of x. Then we can write its joint probability as the multiplication of the functions of the random variables independent. Okay? So that's how you define the joint distribution of these random variables. Okay. So talk a little bit about population samples, why it's important to get unbiased samples, want to make good analysis based on the information we got. So some important statistics. Our main purpose in selecting random samples is to draw information about the unknown population parameters. So, if I'm looking at all the students in Texas State University and I want to find out what is the average performance in terms of the GPA, then I would like to know the mean GPA for all the students. Okay? So that's the type of thing that you want to know. So those are unknown population parameters. You want to find out the average GPA for all the students at Texas State University. I think you can do that with a computer and database. You can go and find out, but it's going to take some time. So you can also take a representative sample and find out about the possible average. So another example is, suppose that we wish to arrive at a conclusion concerning the proportion of coffee drinkers in the United States who prefer a certain brand of coffee. So will you be able to interview all the people who drink coffee in the United States? That's impossible. So it's impossible to question every person in order to compute this. So we can use this estimate, which is the proportion, or an estimate to represent the population proportion. We can take a large random sample and then find an estimate for the population proportion, which in this course we're gonna use this sign to denote that this is an estimate of a real parameter. So this is an estimate of the real parameter. We use p hat in this case. So we're gonna estimate the proportion of the people in this sample favoring a particular brand of coffee. Okay? So p hat, or the estimate of the proportion, is now used to make an inference concerning the true proportion p, which is based on the population. Okay, so now we are trying to estimate some parameters from the population using the sample. We're going to use some estimates. We're going to use a hat to identify those estimates. So many random samples are possible from the same population. So you can take, if you have 100 students, you can take 3 samples of 5 students. You can take 10 samples of 4 students. It all depends on your strategy and how you're going to achieve the objectives. And we're going to talk about that also in this class. So we will expect the proportion to vary somewhat from sample to sample. So we are taking a sample from 100 students, and we want to compute the proportion. Let's say about the coffee drinkers in the university. You will see that from sample to sample, those statistics will be different. Okay, unless you are taking the same students. But if you're taking different students, you will see that your proportion will change. So, p hat value is a random variable that represents the population. Okay, so now you will see that these estimates, these proportion estimates, will be different for each sample. We can treat those estimates for each sample as random variables. Okay, so such random variable is called a statistic. Okay? So now you know what a statistic is. Okay? So we are making inference from samples. We are computing a particular estimate. Those random variables or estimates are called statistics. Any function of the random variables constituting a random sample is called a statistic. Okay? Okay, so in lecture 7, we introduced the 2 parameters, mu and sigma squared. Do you remember what mu means? It's the mean for? It's the population mean. Okay? Sigma squared is the population value. Okay? So now we're going to talk about the population mean, population variance. We're going to also talk about sample mean and sample variance. Those are concepts that are different. The way you compute them is different. Okay? So the mean and the variance, which measure the center of location and the variability of a probability distribution. These are constant population parameters. So once you take into account all the units that constitute the population, you can say that this mean and variance will be constant because they will not change. You are taking into account all the members of the population. So those values, parameters, will be constant and are not influenced by the observation of a random sample. Okay? So now we define some important statistics that describe the corresponding measure of a random sample. So we know how to compute this for the population. Now we're going to show how to compute them for the sample. So the most commonly used statistics for measuring the center of the set of data, remember at least 2 of them, all will be those measurements that we use to measure the center of the data, the mean, and we covered the median. Today we're going to talk about the mode. Okay, so it's going to be the mean, the median, and the mode. Okay, so we're going to add another one, which is the mode. And I think you know what the mode is already. But just a review. So let's say you have n number of random variables. You know how to compute the sample mean. Is 1 over n times the summation of the values of the random variable. And you know how to compute the median, and you know that the median is dependent on the number of observations. So if it is odd, you look at these positions, you sort them, you look at that position. If it is even, your sample, then you need to sort the data points, and you need to find those two positions and average them. Now, for the sample mode, is the value that the sample that occurs most often. So from these, I don't know if you're going to be able to see the numbers back there. So from these data points, can you identify the mode? Yes, correct. That's the only number that is repeated actually from the list. We have 43 once and 42 times, and it's the number that repeats the most from this list. So the mode is 0.42. Questions?
Yeah, we did two repeats. I say 143, 143, and then 147, 147.
Mm-hmm. You have two. Yeah, so you can stay two more. Yeah. Any other questions? Okay. Now, so those are the measurements for the center of location. Now, we also talk about the ones that represent the variability. So those include the sample variance. And look at here, formula for the sample variance has an n minus 1. And do you remember why we subtract 1 from n? It has to do with the degrees of freedom. We are using an estimate to compute another estimate, so we need to take 1 degree of freedom from the number of observations. Okay? So that's why we have n minus 1. Standard deviation is just the square root of this, and the range is just the difference between the maximum and the mean from your observation. So here we have an example just to review how to compute the mean and the sample variance. So we have comparison of coffee prices at 4 randomly selected grocery stores in San Diego. They show increases from the previous month of 12, 15, 17, and 20 cents for a 1 pound bag. And I want you to find the variance of this random sample of price increases. So for that, you need to compute the mean first, right? Because you need the mean to compute the variance. So the first thing you have to do is to sum this and divide by the number of observations. So in that case, that is 16 cents. Now, for the variance, so make sure that you understand how to compute this. I think that I have seen some students making mistakes computing the sample variance. So you're looking at the difference from each point, data point, minus the average square. So we take 12 minus 16 squared, 15 minus 16, and so on, and divide it by a minus 1. Okay, so that's how you compute the sample mean. And we're going to use, you're going to have to compute the sample mean a lot. So make sure that you understand how to compute the sample mean. Questions?
Yeah,
I can post them, but just let me know, send me an email to remind me. Questions? Okay. So now let's talk about sampling distributions. Okay, so we talk about population, how to get samples, has to be unbiased. You know some measures of location, you know some measures of variability. So now let's focus on those distributions first for the mean. So we're going to define a distribution for the mean. Okay, so the field of statistics inference is concerned with the generalizations and predictions. So we are taking a sample and we want to make some generalizations about the population and some prediction as well from the sample to the population. So for instance, let's say you're working at a construction agency and you want to see, say that the average cost to build a resident in a particular city in South Carolina is between 330,000 and 335,000, but this is only based on estimates of 3 constructors, and you know that there's about 30 buildings in that city. So we are only making conclusions from a limited sample of 3 from 30 constructors in the city. So the population being sampled here is again finite but small. So statistic is a random variable that depends only on the observed sample, and it must have a probability distribution. So the statistic that we compute, or we computed from here, is only based on 3 observations from the total population. Again, the statistic will only be dependent on the observed sample. So your statistic will change depending on how you collect the sample and the number of data points in your sample. Okay, so the probability distribution of statistics is called a sampling distribution. So for example, the probability distribution of X bar, which is the sample mean, is called the sampling distribution of the mean. So the sampling distribution of statistics depends on the distribution of the population, the size of the sample, and the method of choosing the sample. So again, you want to be able to choose your sample in an unbiased fashion. So we'll study several of the important sampling distributions frequently used in statistics, and we also study some application of the sampling distribution considered through most of the remaining of this course. So the material we are learning today is going to be used for the remainder of the course. Okay, so keep that in mind. So this is very important. This is like a building block for what we're going to cover next. So again, the material that is left for the class is more theoretical. I'm going to make it as applied as possible, but it involves some details. You need to try to understand those details and try to follow as much as possible. If you have questions, please go to my office, because we're going to be covering some theoretical stuff here. And I'm going to try to apply the concepts as much as possible, but if you still have questions, please try to clarify them. Okay? So the sampling distributions of X bar and X squared, which is the sample variance, are the mechanisms for which we will be able to make inference on the parameters mu and sigma squared. So we're going to use the sample parameters to make inference about the population parameters. In this case, from the mean to the population mean, or the sample mean to the population mean. So the sampling distribution of X bar with sample size n is the distribution that results when an experiment is conducted over and over, always with the same sample size, and many values X bar result. So let's say you have 100 observations. So 100 observations, you can take 10 samples of 5. So how many sample means you will have? Say that again?
10.
10. Correct. Because you're going to compute one sample mean for each sample. So an experiment conducted over and over, always with the same sample size, let's say you're taking 10 samples, will have the many values of x bar result, which in that case will be the same number of samples, same number of x bar. This sampling distribution describes variability of sample average around the population mean. So you will get 10 sample means, all of them with different values. That will give you some idea about the variability of the population. So the same principle applies to the case of the distribution of the variance. So the sampling distribution produces information about the variability of x squared values around the population variance, which is sigma squared in repeated experiments. Okay, so again, the idea is to compute sample average and try to estimate the population average, compute the sample mean and try to estimate the sample, or the population mean. Okay, so now we get to the actual mathematical stuff or computational stuff. So we're going to start looking at some specifics. So let's talk about the sampling distribution of means and the central limit theorem. So the first important sampling distribution to be considered is the mean. So we're going to focus on the mean first. So if we are sampling from a population with a known distribution, either finite or infinite, the sampling distribution of x bar will approximately be normal, with mean mu and variance sigma squared over n. Okay, so this is very important, the mean mu and the variance sigma squared over n. And this. So what we're saying here is, if you sample, let's say you take a large number of samples or group of samples which the sample size is large, let's say over 30, you have 30 samples and you have 30 observations or more on each sample. The distribution, independently of the distribution of the random variables within the sample, the distribution will be always, distribution of the sample mean will always be normal. Okay? And this is an amazing result that is an immediate consequence of the theorem that we're going to discuss next. So a lot of the topics that are related to inference statistics are based on this theorem. Okay? So the sample, you take 10 samples, you compute the sample mean for each sample. The distribution of those sample means will always be normal with this mean, mu, and variance sigma squared over n. Okay? So that is presumed here in this theorem. This is coming from your textbook. So if x bar is the mean of the random sample size n, taken from a population with mean mu and finite variance, then the limited form of the distribution z equals x bar minus mu over sigma over the square root of n, as n tends to infinite, is the standard normal distribution with mean 0 and standard deviation 1. That's the central limit theorem. Okay? And again, most of the material is based on this amazing result. Okay? So the central limit theorem, and this is how we can explain what happened. So let's say that the normal approximation for x bar depends on the sample size n. Okay, so again, the central limit theorem, in order to apply the central limit theorem, you need to have a large number of observations in your sample. Okay, so the normal approximation of x bar depends on the sample size n. So we're going to look at this figure now. So the figure shows that the distribution of tape portrays a 6-side through die. So let's say you only have one die, and you throw that. You only have 1 point every time you throw the die, right? So let's say you have a pair die, and you'll get 1, 2, 3, 4, 5, 6, and you have the same probability of getting one of the alphas. So that is shown here. That's how your distribution is going to look like, because all of them will have the probability. If you compute the mean of each observation, so the mean of 1, only one observation, what will be the mean? 1. The mean of 2 is 2. Mean of 3, only one observation is 3. So that's why this distribution looks like this. Now, if you increase the number of dice that you have, let's say 2, you throw 2, now you will see that if you get 1 and 6, your average will become 3.5, right? If you get 2 and 4, the average will get 3. And if you keep doing that, you'll see that the distribution is going to start looking like this, because the average is going to be concentrating in the middle. You get 3 and 3, the average is 3, you get 2 and 4, and so on. So, if you add more dice in the experiment, you'll see that when you add more, distribution is getting a better shape. And can you guess what type of distribution is that? It's a normal. Okay? So, if you compute the average, and the average is your random variable, as you increase the number of dice that you use, you'll see that the shape that you're going to see is the normal. Okay? So the normal distribution of x bar becomes closer to the normal as n grows larger. And the normal approximation for x bar would generally be good if we have a sample greater or equal to 10. So the sample size n equals 30 is a guideline to use for the central limit theorem. Okay? So if you, again, size is large, you look at the sample, average of the sample, the sample average, you'll see that the distribution of the sample average will tend to be normal. And that's the result of the central limit theorem. Okay, so let's look at how to use this. Now that we know that result, we can solve some problems. So let's start with this one. And then after this one, you're going to have a chance to show me that you can do this with the lab. So it's going to be a very similar problem. So if you follow what we're doing here, you should be able to solve the problem in the lab. And you're going to see that it's going to be very similar. Okay, so let's look at this. An electrical firm manufactured light bulbs that have a length of life that is approximately normal distributed with mean equal to 100 hours and a standard deviation of 40 hours. I want to find the probability that a random sample of 16 bulbs will have an average life of less than 775 hours. Okay, so let's define the sampling random variable. So the sampling distribution of x bar will be approximately normal with mu x bar equals 100 hours. So we know that. And how can you compute the sigma of x bar? From the So the sampling distribution of x bar, we have a mean of mu, that is sigma squared over n. Okay, so let's use that result here. So this is sigma over square root of n. So this is 40 over square root of 16, and this is 10. So we know average life, this is the probability that we want to find, less than 775 hours. So average life of 775 hours. So we can use a standard normal transformation. So z will be equal to 775 minus 800 divided by 10, and that will be equal to 2.5. So the probability of x bar being less than 775 is going to be equal to the probability of z being less than minus 2.5, which is equal to 0.6062. So the probability we are looking, if you look at the graph here, is this area. And we can use the standard normal transformation because we know that the distribution that the sample average will follow is normal based on the central limit theorem. So that's why we use the normal, because now we know that if we look at the distribution of the sample, and here we're looking at the average life, we know that that random variable follows a normal distribution. So we can use the normal transformation to solve the problem. And this is the shape of the distribution. We're looking at that area. Questions? Okay, so I know it takes some time to digest, but let's try. Again, the next problem is very similar, so I want you to try it, because if you don't try it, I don't see if you are learning or understanding the material. So again, these labs are not for, it's to help you learn and also to help you in your grade. If you're here in class and you solve the lab, you'll see that the labs are going to work together. The lab will give you an extra boost of your final grade is how to decrease the force. That's if you come to class, okay, and you solve the lab. You know, if you're not in class, you get the 0. That obviously will affect your grade. So, you work with this, with them. So just follow the problem we discussed, and you should be able to solve this problem. If you don't have the table, the normal table with you, I have some copies with me, so I can provide you the table. So the equation.
Yeah, 100. Yeah.
Oh, yeah.
Yeah, new experts.
It's different.
Yeah, we did that. That was our snake.
800. Yeah.
95 minus
100.
Actually, if you solve the problem, you will see that you will get to this number. Okay, so you will not need the table at all. So, are you done? Should give you 2 more minutes. Yes, 2 more minutes. Yes. So I will collect the problems and discuss and then pass the exams. If you're done, start passing your papers to this side. Okay, so let me discuss the problem and then I'm going to pass the exam. So I have all the papers. Do I have all the papers with me? Okay. So, very quick. So, what we have here is the following. We have mu equals mu x bar, which is 100 ohms. We have sigma x bar equals sigma over n, square root of n. So this is 10 over 5. This is 2. X bar equals 95. C equals minus 2.5. And the probability of x bar being less than 95 equals the probability of z being less than negative 2.5, and this is equal to 0.0062. Okay, so now I'm going to pass the exams. Any questions?